In this lecture, I want to introduce you to the mathematical concept of sequences. Have you ever wondered how we can calculate the value of e or pi to any given accuracy? For pi, one way to do this is by writing it as the following infinite sum. Pi is equal to 4 minus 4 over 3 plus 4 over 5 minus 4 over 7 plus 4 over 9 minus 4 over 11 plus 4 over 13 minus 4 over 15 plus, and I hope that you see the pattern here. So what is happening here is that all the terms have the following makeup. It's 4 over and then an odd number, and then the first term is positive, the second term is negative, the third term is positive again, and so that alternates throughout this sum. Now, the elements or the terms of this infinite sum are called a sequence. And if we want to define that more formally, a sequence is a function from the positive integers to the real numbers. So if we look at the previous example, we can write down the first 5 elements of our sequence or our function. So for the input n equals 1, the first element of our sequence is positive 4. Then the second element of our sequence, f of 2, is negative 4 over 3. And then the third element is positive 4 over 5. And the fourth element is negative 4 over 7. And then the fifth element, f of 5, is given by 4 over 9. Now, instead of writing out f of 1 equals 4, f of 2 equals negative 4 over 3, we use the notation a sub 1 stands for f of 1, a sub 2 stands for f of 2, and we can denote the entire sequence by a sub n with curly braces around it. We can also write it out as follows: a sub 1, a sub 2, a sub 3, and then etc. We just continue that infinitely long. Now note that the order is important for sequences. Now let's look at a couple of examples. Write down the first 5 elements of the given sequence. So the first sequence that we're looking at is the sequence a sub n given by 3 plus negative 1 to the power n. So we can take a look at a sub 1. And a sub 1 is equal to 3 plus negative 1 to the power 1. And so that gives us 3 minus 1, and that is equal to 2. A sub 2 is equal to 3 plus negative 1 to the power 2. And so that is 3 plus 1, and that gives us 4. And then a sub 3 is equal to 3 plus negative 1 to the power 3. And that is equal to 2. Two more to go. A sub 4 is equal to 3 plus negative 1 to the power 4, and that gives us 4. And then finally, the last one, a sub 5 is equal to 3 plus negative 1 to the power 5, and that's 3 minus 1, so that gives us 2. And so the first 5 elements of the sequence, we can write it as 4. Sorry, we have to start with 2. So a sub 1 is equal to 2, then a sub 2 is 4, then we have 2, then we have 4, then we have 2, etc. So what we see here is that the whole sequence is an alternate collection of 2s and 4s. Okay, the second example, the sequence b sub n is given by -1 to the power n minus 1 times 4 over 2n minus 1. So let's write that one out. So we have b sub 1 is equal to -1 to the power 1 minus 1, and then times 4 over 2 times 1 minus 1. So we have 1 minus 1 in the exponent here, and then in the denominator 2 times 1. So b sub 1. So when you simplify that, -1 to the power 0, that gives us positive 1. So that's just a positive 4 over 1. So that's 4 over 1, or just 4. Okay, now let's take a look at b sub 2. That's -1 to the power 2 minus 1 times 4 over 2 times 2 minus 1. Okay, so we get -1 to the power 1. That gives us a negative. And then we have 4 over 2 times 2 minus 1. That gives us 3. So we have -4 over 3. What about b sub 3? b sub 3 equals -1 to the power 3 minus 1 equals 4 over 2 times 3 minus 1. So what we have here is b sub 3 is 3 here and a 3 here. And I forgot my 2 here for the b2. So b sub 3 simplifies 2. This is going to be positive. Oh, and I shouldn't have put an equal sign there. So this is equal to positive 4 over 5. That's b sub 3. And then b sub 4 is -1 to the power 4 minus 1 times 4 over 2 times 4 minus 1. b sub 4. And what we see here is the -1 contributes a negative sign here. And then we have 4 over 7 as our final answer, -4 over 7. And then finally, we need to find b sub 5. That is -1 to the power 5 minus 1 times 4 over 2 times 5 minus 1. And what this simplifies to is a positive 4 over 9. Okay, so if we collect all the terms or all the parts of our sequence, we get 4, -4 over 3, 4 over 5, -4 over 7, and then 4 over 9. And then that sequence continues indefinitely. And this is actually the sequence that we started the lecture with. Another way to define sequences is by using a recursion. So the way that works is you start with one number in your sequence, C1, and then you define the other terms in your sequence by writing Cn plus 1 in terms of Cn. So Cn plus 1 is defined in terms of Cn. And sometimes you can have recursion that goes back more than one step. So you could also have Cn minus 1, Cn minus 2, etc. If your recursion goes back more than one step, though, you need 2 or 3 starting numbers in your sequence. So you might need C2 and C3 as a given. So now let's take a look at C2. We already have C1. So C2, what we have to see here is that that 2 plays the role of n plus 1. So quickly, if we have n plus 1 equals 2, right, the subscript here, we can subtract 1 on both sides, and we actually see that that means that n equals 1 in our formula. So C2 is actually C sub 1 plus 1. And so this is equal to C1 squared plus 2 over 2 times C1. So again, I'm using n equals 1 for C2 in the formula. And now we can plug in what we know for C1. Right, C1 is 1, so we square that, we add 2, and then we divide by 2 times 1. And that value gives us 3 over 2. Okay, now for C3, we do something similar. We take C3 is C sub 2 plus 1. So for C3, we have that n equals 2. So C2 plus 1. And in our formula to find C3, we use n equals 2. Because if you have n equals 2, that gives you C3. So now we have C2 squared plus 2 over 2 times C2. Now C2 is 3 over 2 squared. We add 2 to that, and then we divide by 2 times 3 over 2. And I won't bore you with how to simplify this. It simplifies to 17 over 12. Which is approximately equal to 1.417. Now, C4 works the same way. So C4 is then C3 plus 1. And you can check my math here. If you plug that in, eventually you get that C4 is 577 over 408. And that is approximately equal to 1.4142. And then finally, C5, that would be C3 or C4 plus 1. And if you do that, we take this, we square it, we add 2, and then we divide by 2 times this value. And at that point, it doesn't really make sense to write it as a rational number, and we can just write down the approximation of this as a decimal number. And it turns out that C5 is approximately equal to 1.4142, 13562. And this is actually a special value that this sequence converges to. Because if you put this into your calculator, square root of 2, you see that square root of 2 is approximately equal to 1.4142135562. So after 4 steps, or looking for the 5th element of this sequence, it already has square root of 2 approximated to 1, 2, 3, 4, 5, 6, 7, 8, 9 correct digits. Now, it's not exactly equal to square root of 2, but if you keep repeating this process, you get infinitely close to square root of 2.